The next speaker is Carlo Cannarozzo, charting the back-in-time evolution of the scaling relations of early-type galaxies over the last 12 billion years.
Can you hear me? Oh. Okay. Hi everyone. I am Carlo Cannarozzo, postdoctoral researcher at New York University, but in its declination, the exotic one in Abu Dhabi. And today I would like to talk about early-type galaxies, and in particular how some scaling relation in early-type galaxies evolved through cosmic history. Of course, I don't have to tell you how complex is the formation and evolution of galaxies, right? It takes billions and billions of years. We know that after the Big Bang, from an homogeneous distribution, dark matter started to collapse into a complex structure that we call cosmic web. Gas all this trend formed the first galaxies. Galaxies accreted gas in the surroundings, interacted with other galaxies. Also, there is the supermassive black hole that, through its radiation, is able to blow out part of the gas and causing quenching. And after billions of years, you end up with these huge monsters that are early-type galaxies, which might be very massive, right? But the key aspect of all this process is one, which is gravity. Gravity is able to install in galaxies some relation between physical properties. And of course, we know since the late 70s that there are relations involving the luminosity, or we can represent easily stellar mass, with the velocity dispersion through the Faber-Jackson relation, with the Cormender relation between luminosity and size. And soon thereafter, in the 80s, it was found that these are just two simple projections of a more complex relation, which is a plane where all early-type galaxies, at least at redshift 0, lie, which is the fundamental plane. And with the improvement of technologies, actually, we have been able to look further and further in the universe to check whether and to what extent these relations are still there. And actually, they are there. And actually, they do evolve as a function of time. For instance, this one is the size-mass relation from Van der Waals 2014. What we can see is that at fixed mass, galaxies in the present-day universe are larger than their counterparts at high redshift. And there are some hints also for the evolution of the stellar mass velocity dispersion relation. And so the question is how, for instance, a galaxy at a given redshift, here we have the stellar mass velocity dispersion plane. I drawn two qualitative relations between the stellar mass and the velocity dispersion, how this galaxy can move to reach the functional form at redshift Z1, right? Of course, there is the assumption that this galaxy won't move to the right for you because of mergers, right? And we have more or less three possible ways, right? Maybe increasing its velocity dispersion, maintaining the same, or decreasing its velocity dispersion. In 2020, in collaboration with Sonnenfeld and Nipoti, we provided for the first time a description, a continuous description, by Bayesian hierarchical approach of how this relation evolved continuously from redshift 0 out to redshift 2.5. And among all the models that we tested, we found that these two descriptions are the best. On the left-hand side, you have a constant slope model. On the right-hand side, you have an evolving slope model. Here I've drawn 5 curves from redshift 0 out to redshift 2. But as I was saying, this is a continuous description, so if you want, you can put your redshift and you can end up with your relation. Of course, there is a clear evidence for the evolution of the relation. And so now, again, the question is, if I have a galaxy at like, I don't know, redshift 1, how it evolves to reach the functional form at redshift 0? Qualitatively speaking, here we can identify two possible regimes. Indeed, below 10 to the 11.5, a galaxy at redshift 1 can reach the functional form at redshift 0, increasing, maintaining, or decreasing its velocity. But this scenario is no longer available if we want above. We go above 10 to the 11.5, which necessarily this galaxy must reduce its velocity dispersion to reconcile with the functional form at redshift 0, because otherwise it reaches stellar masses which are not allowed, right? But now I want to be more quantitative than this. So what I'm going to do is to combine this kind of inference of the relation with theoretical models. These are, today I'm going to show you some preliminary results about Empire. Empire is a semi-empirical model that Aldo Rodriguez-Puebla has been developing. And also in the future, I'm going to use Ni-Hao simulation. The mean simulation is now I'm part of the group there. And the law. LO is a new Ni-Hao-like simulation focused at redshift 2, 3. In my work of 2020, my sample was quite smaller, in the sense that I was focusing above 10 to the 10.5 solar masses and out to redshift 2.5. And now I'm enlarging my sample at redshift 0. My sample in stellar mass is wider, for above 10 to the 9 solar masses. And also I collected a lot of galaxies at higher redshift that in the last 3-4 years came out. Last but not least, these recent galaxies from the WSP excels south. So now my range at redshift 0 is above 10 to the 9 solar masses, and the redshift is from 0 out to almost 5. However, if I plot the distribution of the stellar mass velocity dispersion and stellar mass size at least below 0.2, we define these bendings, these banana shapes, right? And there are some hints for 1 or maybe 2 characteristic masses that occur around 3 times 10 to the 10 solar masses and 2 times 10 to the 11 solar masses. Of course, this one is not surprising, because previous results showing this kind of bending already Heide Bernardi with in 2009 using SDSS modeled this evolution, modeled this relation with a parabolic model. Capellari using Atlas found this double power law model, and recently Quenneville using massive galaxies, which are very massive systems, found that maybe these relations show another characteristic mass. So these two relations are even more bent. And the other question is, these relations here are at around redshift 0. What about higher redshift? Of course, we have at least for the size-mass relation a plethora of results showing that these bands are still there at higher and higher redshift. Unfortunately, there is a lack of studies about the stellar mass velocity dispersion relation at high redshift, because, I mean, you need reliable velocity dispersion measurements, so you need reliable spectra to infer the velocity dispersion, and so reconstructing the evolution of this relation. So what I'm doing now is to enlarge my view, not limiting my analysis only to the stellar mass velocity dispersion relation, but also to the stellar mass size, the fundamental plane, and the stellar mass fraction, to have a more complete view. And in particular, what I'm doing is with my Bayesian hierarchical approach, I improved this tool, and I'm considering a model that is made of a triple power law, another one that is a more classical view, which is the double power law. Then I'm analyzing also the fundamental plane, which can be just one for all the galaxies at all redshift, a fundamental plane which evolves in normalization, and a fundamental plane which evolves both in normalization and slope. And last but not least, I'm also modeling the stellar fraction within one effective radius, again as a constant model, as a model which evolves in normalization and a model which evolves both in normalization and the characteristic map with the relation map, right? And among all these models, these are the new brand results. On the left-hand side, you can see this new stellar mass velocity dispersion relation. On the right-hand side, you have the stellar mass size. And again, as I was saying before, we define these two characteristic masses as around 10 to the 10.2.3 and 10 to the 11.5, 10 to the 11.6. And these results actually are remarkably in agreement with, in a remarkable agreement with many other previous results. And what about all the other relations? If I collapse there in a fundamental plane, actually I do find that the fundamental plane shows a slightly evolution in its normalization. And there is the stellar mass fraction within one array. What is informing this plot? This plot is saying us that at fixed stellar masses within one array, within one effective radius, in the past there were a larger contribution of stars than dark matter, right? So basically, at fixed mass, there is a higher concentration of stars within array than today. Okay. But okay, let's come back to the previous question. The previous question was, I would like to provide a quantitative description of how these galaxies evolve, track the evolutionary pathways of individual projects. And to do that, as I was saying, I will use in the next future the Niao and the Hello simulation. But today I'm going to show you some results from the semi-empirical tool that Aldo has been developing, called Empire, sorry. Empire is this semi-empirical tool having many observational ingredients. There are size mass function, a stellar mass function at different redshift, and many of them are listed there, and many others. The theoretical ingredients inside Empire are the dark matter only simulation. So the idea behind Empire is that you are able to trace the mass assembly history of the dark matter here, right? So you assign with a given probability a given galaxy to a given halo. You produce a galaxy in a given halo. Following the mass assembly history of the halo, you are following the history of the whole galaxy and the physical properties and how they work. And so if I use Empire, this is how the evolutionary tracks look like for the stellar mass velocity dispersion relation. Let me drive through. The relation is the same that I showed you before. Here at redshift 0, I picked up 11 random galaxies from A to K. Here, these colored shaded regions are marking 80% of the progenitors. So all these progenitors assembled together, merged together, and we end up with these galaxies in the purple color. Okay? Here you can see this gray band here, and this gray band is marking a crucial aspect in the galaxy evolution. It's basically the progenitor bias. It's tracing the progenitor bias. So a galaxy that today is an early type galaxy, maybe in the past is the remnant of the progenitors, of course, might be early type galaxies as well. But maybe in the past, some of their progenitors started these performing galaxies. So everything that is below this gray curve basically are at least 50% of the progenitor at early type galaxies. But coming again to the tracks, what I do find are three regimes, more or less similar to the ones that I was describing before. At low mass scale up to more or less 10 to 10.5, we define that the stellar velocity dispersion tends to increase as function of more at 10 to the 5, 10 to the 11, 10 to the 10.5, 10 to the 11, velocity dispersion is almost constant. Instead, for very massive galaxies where there is the flattening in the relation, the velocity dispersion decreases. And if I analyze, for instance, the mass assembly history of these galaxies and the contribution of in situ and ex situ stellar components, properly where the flattening occurs, you can see that the FC2 component becomes more and more relevant, like 60, 70, 80% or 90% in the most massive galaxies of the total stellar mass, which means that these galaxies underwent during their history, during their cosmic history, a lot of minor movements. Understanding finally what bends and what are the physical reasons for the evolution of this relation is not trivial at all. Of course, we have previous studies suggesting that these galaxies there is a morphological transition at low mass regime from star forming towards early type, and the other transition from like fast rotators to slow rotators. But there are also other effects like the mass-to-light ratio variation, as we saw today also from Roberto Cavicciai's talks, the evolution, the mergers of supermassive black holes, the environment, and many other things. Of course, likely, Empire, Loni, House simulation, and other theoretical models will come to my rescue to find a possible solution to this. So I think that I concluded here. I leave you here with my conclusion, and let it take you. Thank you very much.
We have time for a quick question.
Thank you. I have actually two questions. The first is because you were showing the model about early type galaxy evolution. So I simply wonder, have you considered the effects of like mergers that destroy the disk and turn it into early type galaxies, or is simply a secular evolution of early type galaxies?
The official answer is no. But of course, as I was showing you before, here here below this track, there are the majority of the progenitors are early type galaxies, as I was saying. Above this track, these are disks and star-forming galaxies, right? But I have to say that also star-forming galaxies should lie on another relation. So as I'm saying here, as a next step, actually, what I want to do is to enlarge my view also including star-forming galaxies to have a more complete view of what's going on. But this would be the next.
Yeah. And my next question also related to this, because you just say some galaxies on this dispersion versus mass would decrease their dispersion. So what is the mechanism that you would propose to decrease their dispersion?
As I was showing you before, those galaxies should lie in these regimes here, right, where there is the transition from fast and slow rotators. And of course, as I was showing also with I have not shown here how many mergers they experience, but all these galaxies experience in the very past a lot of major mergers and a lot of minor mergers. So the contribution, of course, of mergers are in these kind dry mergers. Focus on dry mergers are one of the possible responsible for this. Of course, there will be the action maybe of the central supermassive black hole, and it's something that I'm going to explore next week of Vision 5.
Thank you.
Okay, let's thank Carlo again, and the next speakers should move.